Hello everyone, welcome to the NPTEL course on computer process design. In the last class we started looking at mass balance equations for different equipments. We have started with mixture unit, then we have extended our analysis to splitter unit, then we have looked at reactor unit, then we have seen the flash unit, uh, then after that we have looked at the distillation unit and then absorption unit and finally the splitter unit. So these are the different equipments which we have seen in the last class. Okay, so how these concepts of linear mass balance is then combined in a flow sheet, that is what we are going to look at today. Okay, so in this case, let us start with the discussion on these linear mass balance equations which we have obtained. So the development of unit models is a key step in the linear mass balance algorithm. So because of that, we have uh, formulated the linear mass balance equations for different units. Then the unit models involve approximating each unit with split fractions representing the outlet molar flows linearly related to the inlet molar flows. The linear equations for each unit are combined to solve overall mass balance. The temperature and pressure are then set and the energy balance is calculated. The assumptions made in the development of unit models include the assumptions that all vapor and liquid streams have ideal equilibrium relationships and that all the streams are at saturated conditions. Again, the physical properties can be calculated easily from the standard data available in the handbooks, and calculations are very easy to set up and solve with the few iterations required for convergence of a preliminary design. And the last point here is the linear mass balance algorithm is a powerful tool for evaluating mass and energy balances for candidate flow sheet, but it makes several ideal assumptions that may lead to inaccuracies in the final flow sheet. But anyway, once this preliminary flow sheet is obtained, then we can refine this mass and energy balance equations and then uh, come up with the final design. So if you look at the different units, so if you look at the splitter unit or the reactor unit or the distillation unit, absorption unit and the stripper unit, in these different units there are different degree of freedom involved. For instance, in a splitter or in a splitter the degree of freedom is just one, so we have to just specify the split fractions, whereas in the reactor typically the conversion is important, because that based on the conversion we are finding out how much will be the molar flow rate of the different components coming out from the reactor. If you look at the flash unit, in the flash unit the degree of freedom is 2. So in addition to the split fractions, we have to either specify temperature or pressure. When we go to the slightly complicated uh, units like distillation, in distillation degree of freedom is 3. So there, in addition to the split fractions, we also need to specify temperature, and also we need to specify the number of stages involved. When we look at slightly one more complicated units like absorption unit or a stripper unit, in a absorption and a stripper unit the degree of freedom is 4. There we need to specify pressure, temperature, we need to specify the split fractions, and also we need to specify the absorption factor. So these are the 4 degree of freedom required. So typically how we solve each of these units is we take the initial case of pressure and temperature for different units in the flow sheet. Also we specify the recoveries, split fractions depending on the degree of freedom. Then we determine the different unknown coefficients such as relative volatilities. We also find out the number of stages, coefficients used in the linear mass balance of each unit. So when I'm saying the coefficient, these are the coefficient like beta n and beta n minus 1. This type of coefficients we can find out, and then we can solve this set of linear equations and we can obtain the flow rates for each component. Once the flow rate of each of the components are obtained, then we have to check whether the assumed values of temperature, pressure and the split fractions are actually satisfying these or not. So what we do is, based on this flow rate, we again calculate pressure and temperatures, and if these values are different from the step 1 which we have assumed, in that case what we have to do is, we have to again go back to the step 2 and do the all calculations here. If the desired constant of specifications are violated, in that case we have to change the temperature and pressure, and we have to solve this entire procedure one more time. Okay, so we can appreciate these concepts if you look at one simple example. So in this case, let us take an example of the same case study which we have seen in uh, the uh, preliminary flow sheet design. So in this particular case, what we are looking at is, let's say if there are 100 mole per second for ethylene feed is there, uh, and we wanted to perform the mass and energy balance with the same ethylene to ethanol production flow sheet. The components present in the flow sheet are methane, ethylene, propylene, diethyl ether, ethanol, isopropanol and water. There is also a crotonaldehyde is there, but the amount of crotonaldehyde produced is very small, so we can neglect that. So in this case, the methane is represented by M, ethylene is represented by EL, propylene is represented by PL, diethyl ether is represented by DEE, and ethanol is represented by EA, isopropanol by IPA, and water by W. So in this case, you can see that uh, if you look at the flow sheet, this is the same flow sheet which we have obtained. So you can see that we can represent the notation for each of these molar flow rates. So for instance, the molar flow rate of the water feed is mu 01, uh, molar flow rate of the ethylene feed is mu 02. Again, this water and ethylene is mixed with the recycled components, and these are mixed in the mixture, and the entire mixture will have a molar flow rate of mu1. So this entire molar flow rate of mu1 is then charged to the reactor, and in the reactor, due to different reactions, we will get the different molar flow rate, let's say mu2, and then the reaction mixture coming out from the reactor is then charged to the flash unit, where the temperature is reduced to a cooling water temperature, and the liquid stream and the vapor stream is separated. So vapor stream separated is represented by mu31, whereas the liquid stream separated is represented by mu32. So this vapor stream coming out from the flash unit then charged to the absorber unit, where the key component like ethanol is absorbed by using the water. So the fresh water which is charged to the absorber unit, the molar flow rate of that is mu 03, and the vapor coming out from the absorber is then sent to the splitter unit, where some uh, uncondensed gases, some impurities are removed as a purge stream, and the molar flow rate of that purge stream is given as mu 52, whereas the recycled stream coming out as mu 51. So you can see that uh, similar to this vapor loop here, the liquid also coming out from the flash unit is then mixed with uh, the ethanol rich water stream which is coming out from the absorber, and this water rich stream is then charged to the first distillation column, which is essentially a dewatering column. So here primarily we remove the water, and the ethanol rich stream is coming out as a uh, distillate, and this ethanol rich stream from the top is then charged to the de-ethering column, where diethyl ether is removed, and this diethyl ether is then recycled back to the mixture, uh, whereas the bottom product, which is primarily the ethanol rich stream, this ethanol rich stream is then charged to the last column, where the ethanol water azeotropic mixture is separated as mu 91, and the water waste is separated as mu 92. So this is the entire flow sheet. now we wanted to apply the concepts of linear mass balance which we have looked at with respect to each of these units. So we started with a mixture. So let us look at how the mass balance for the mixture we can represent. So you can see that primarily in the mixture the input is mu01, mu02, mu51 and mu81. These are the input coming in the mixture, whereas the output coming out from the outlet coming out from the mixture is mu1. So we can represent the mass balance for the mixture easily. So you can see that the mass balance here is given by mu01 plus mu02 plus mu51 plus mu81 equals to mu1. So you can see that with respect to each unit the subscripts are used here. So output from the unit 1 is represented as mu1, output from the second unit is represented as mu2, etc. Then the next unit is a reactor. So as I said earlier, in the reactor conversion is important and there are three reactions occurring in the reactor. So the first reaction is ethylene reacting with water producing ethanol. The second reaction is propylene reacting with water to produce propanol, isopropyl alcohol. And the third side reaction here is ethylene can react with itself to produce diethyl ether and water as a product. So you can see that in this case the third reaction is a equilibrium reaction. So we can represent this third reaction in terms of the equilibrium relationship, and here we can represent this as molar flow rate of diethyl ether into molar flow rate of water divided by square of the molar feed rate of ethyl alcohol, and that we wanted to maintain at 0.2. Okay, so with this now we can simplify the equations for the reactor. And remember in the last session on the preliminary flow sheet design, we said that the conversion of ethylene to ethanol, single pass conversion of ethylene to ethanol is 7%, whereas the single pass conversion of propylene to isopropanol or isopropyl alcohol is 0.7%, and this we can represent by eta 1 and eta 2. We can use these conversion values and based on that we can write down the mass balance equations. So in this case you can see that in the reactor only the ethanol is reacting. So remember the feed is comprised of what? Feed is comprised of methane, uh, ethylene and propylene. So ethylene is around 96%, propylene is around 3%, and methane is there 1%. Okay, so now in this case you can see that since methane is unreacted, so whatever the methane flow rate is their input to the reactor, the same will be the output. So inlet feed rate of the methane will remain same here. So you can see that whatever the methane is charged to the reactor, the same will come out from the reactor, whereas for ethylene some amount of ethylene will get converted to products, and therefore the unreacted ethylene coming out from the reactor will be given by 1 minus eta 1, where eta 1 is nothing but the conversion of ethylene. So this will be the amount of ethylene coming out from the reactor 1 as unreacted component. Similarly, the propylene coming out from the reactor will be 1 minus eta 2 into mu1 PL, where mu1 PL is nothing but the amount of propylene charged to the reactor, whereas eta 2 is nothing but the conversion of propylene to isopropyl alcohol. Now, in addition to these three equations, we can now write the equation for diethyl ether. So amount of diethyl ether coming out from the second reactor, we can write that using the equilibrium relations. So that comes out to be 0.2 mu2 Ea square divided by mu2 W. So this particular relation is primarily coming from the same equation here. So here we are interested in finding out what will be the molar flow rate of diethyl ether coming out from the reactor. So that we can represent as 0.2 into Ea square by W. Okay, so that is what is written here. Now these are with respect to the reactant. Again we can write down the relations with respect to the products formed. So in this case the product formed is ethylene to ethyl alcohol. So molar flow rate of the ethyl alcohol coming from the reactor will be whatever the molar feed rate of the ethylene to the reactor 1 is multiplied by the conversion plus mu1 Ea is nothing but what? Mu1 Ea is nothing but the ethyl alcohol which is charged to the reactor as a feed, and this could be coming through a recycle stream, of course very in a very small amount. We can take this as 0 also. So the another product flow rate we can write down as mu2 IPA. Mu2 IPA is nothing but the uh, molar flow rate of isopropyl alcohol coming out from the reactor, and that will be given by eta 2 into mu1 PLs plus mu1 IPA. So this mu1 IPA is nothing but the isopropyl alcohol present in the feed to the reactor. Similarly, mu1 Ea is nothing but the ethyl alcohol present in the feed which is charged to the reactor. Water, if you look at the water, for water the amount of water coming out from the reactor will be mu1 Ws, that is nothing but the molar feed rate of the water to the reactor minus the amount of water which is utilized in the first reaction and the amount of water which is utilized in the second reaction. So that is what is represented here as eta 1 mu1 El minus eta 2 mu1 Pl. Okay, so note down that when we discussed that particular flow sheet, we said that water is going to be the limiting element. Primarily, we will be using 0.6 ratio of water to ethylene, isn't it? But in this case, in order to simplify the calculation, since water is going to be recycled back, in order to simplify the calculation using the ethyl alcohol and using the ethylene and propylene as a limiting component is simplifies the analysis significantly. So next unit is a flash unit. So in this unit the effluent mixture from the reactor is separated into liquid product and reactant gases by cooling at cooling water temperature of 310 Kelvin. So in this process a pressure drop of 0.5 bar is assumed and the operating pressure of the flash unit is 68.5 bar. Remember that the pressure maintained inside the reactor is 69 bar. So we are assuming that 0.5 bar will be the pressure drop taking place in the flash unit. So that's why the pressure used in the calculation is 68.5 bar. Further, we are assuming that the diethyl ether is taken as the intermediate key component. So diethyl ether is a intermediate key component, and based on that we are now going to find out the components which will be in the top product and the components which will be coming in the liquid stream. Okay. The relative volatilities of the component list and is calculated at the cooling water temperature. So you can see that we are assuming that the split fraction of diethyl ether equals to 0.5. So we are assuming that the 50% will be present in the vapor phase and 50% will be present in the liquid phase. The liquid coming out from the flash unit and the vapor coming out from the flash unit. Now with respect to this, if we take this diethyl ether as a key component, we can calculate the split fractions of other components, isn't it? So in this case there are different components and these are arranged in order of decreasing boiling point. So you can see that we can calculate the vapor pressure of each of these components by using the Antony equation, isn't it? So for water, isopropyl alcohol, ethyl alcohol, diethyl ether, propylene, ethylene and methane, for all these components we can calculate the vapor pressure, and the vapor pressure of the component divided by the vapor pressure of the key component, which in this case is a diethyl ether, that is going to give us the relative volatility. So this alpha k slash dE, this we can obtain directly by using the vapor pressure, and the vapor pressures we can calculate by using the Antony equation for a given pressure and temperature. So in this case, the relative volatility is, if you do the calculation, comes out to be 0.057, 0.091, 0.138. 1 will be for diethyl ether, 13.8 will be propylene, 67.3 will be ethylene, and for methane that will be 256.1. So you can see that predominantly in the vapor stream, primarily we will have propylene, we will have uh, uh, ethylene, and we will have methane, and also some amount of uh, ethyl alcohol. Now based on this, based on the relative volatility and the split fraction of the key component, which is diethyl ether, we can put those values here and we can calculate what will be the split fractions of each of these components, and these split fractions are calculated here. So you can see that predominantly ethyl alcohol, diethyl ether, propylene, ethylene, and methane will be there in the vapor stream. Now with respect to these values of split fraction, we can now write down what will be the molar flow rate of different components in the vapor stream as well as in the liquid stream. Remember, in this case, in a flash unit we get a vapor stream which is mu 31, and the liquid stream we are getting which is mu 32. In both these stream, what will be the molar flow rate of each of these components, that we can directly obtain based on the split fractions. So for instance, in this case, what will be the molar flow rate of uh, methane in the vapor stream, that we can directly calculate as its split fraction multiplied by mu 2m, isn't it? So that is 0.996 into mu 2m. Similarly, uh, uh, this will be the methane which is present in the vapor stream, and what will be the methane present in the liquid stream? Liquid stream, this will be 1 minus zeta m into mu 2m, isn't it? So 1 minus zeta m, so 1 minus 0.996, so that will be 0.004 into mu 2m. Okay, so in this manner we can calculate the molar flow rate of all the components starting from methane, ethylene, propylene, diethyl ether, ethyl alcohol, isopropyl alcohol, and water. All these streams we can calculate both in the vapor phase as well as in the liquid phase. So remember that the vapor stream coming out from the flash unit is then charged to the absorber, where we wanted to recover the uh, ethanol, isn't it? Remember, in this case, if you look at, see, ethyl alcohol around, so ethyl alcohol will also be there in the vapor stream, so that is given as 0.121 mu 2 ea. So so this ethyl alcohol we wanted to recover completely, so we, in order to recover the ethyl alcohol from the vapor stream, we are using the absorber. So in this case, a pure water will be counter currently fed from uh, uh, the in the absorber unit, and this water is going to absorb the ethyl alcohol which is present in the vapor, and this water stream involving the ethyl alcohol is then mixed in the mixture there, isn't it? So in this case, in order to do the calculation, remember that absorber unit, there are 4 degree of freedom, isn't it? So we have to first specify pressure, we have to specify temperature, and in addition to that we have to specify the component recovery. So in this case, the component recovery will be ethyl alcohol recovery, and also we have to specify either the liquid rate or the absorption factor. Okay, so we can calculate this liquid rate using the absorption factor. A typical value of absorption factor used is 1.4, but if you take this absorption factor of 1.4, in that case you will see that the amount of liquid required is very less, and if you calculate the fraction of the liquid which is vaporizing and going along with the vapor, that becomes significant. So and that may lead to the, variation in the temperature, and we wanted to have isothermal temperature in the absorber. So because of that, we wanted to have a higher liquid rate. So instead of using the absorption factor of 1.4, we can use the absorption factor of 10, and with that we will have a sufficient liquid rate and with the sufficient liquid rate, even though some amount of liquid is getting vaporized along with the vapor, but that fraction will be reasonably less compared to the total liquid rate, and therefore we can assume that the absorber is at the isothermal condition. So in this case we can take the AEA, which is nothing but the absorption factor equals to 10. We are also using the temperature of 310 Kelvin and the pressure of 68 bar. So in this case we are also assuming that 0.5 bar pressure drop is happening in the absorber unit. So with the assumption that the split fraction of the ethanol, let's say that is we have fixed as 99%. So that means what, 99% of the ethanol which is there in the vapor stream we wanted to absorb by using the water. So with these values given, you can see that pressure we have fixed the temperature, we have also fixed the split fraction of the uh, component here, and also we have fixed the absorption factor. So all 4 degree of freedom we have fixed here, and now we can do the calculations uniquely. So in this case absorption factor can be represented as liquid molar flow rate divided by vapor molar flow rate into uh, equilibrium constant KEA. So in this case we can obtain the KEA directly by using the vapor pressure, isn't it? So by using the vapor pressure we can calculate the KEA, and also if I put the values here, then remember this AEA value is 10. If I put that value 10 here, so I can obtain L as 10 into VKEA. KEA value we can directly obtain, isn't it? So we can get, and this V is nothing but what, mu 31. Remember, whatever the vapor charge to the absorber is nothing but what, mu 31. So we can obtain the expression of L naught, or mu 03 in a way, isn't it? So in this case the L naught will is nothing but what, 0.0225 mu 31. One more thing to note down here is once we have obtained this absorption factor, then we can use in this Kremser equation, and we can calculate the number of stages required. So in this case you can see that this is the simplified equation. If I go back, remember in the absorption we have given the simplified equations for calculating the number of stages. So when we are assuming that there is no key component present in the liquid, in that case L naught n is 0. So in that case this particular equation is simplified. So the simplified equation is given by, I'll just go back. So simplified equation can be given by R minus AE divided by minus AE into 1 minus R divided by ln AE. You can see that this equation we can directly obtain from the original Kremser equation. So here L naught n, if this particular value, this particular term is 0, in that case this is 0, this is 0, and this V n plus 1 will get cancelled out. So what we get is n is given as ln R minus AE divided by minus AE 1 minus R divided by ln AE. So the same equation we are using for the absorption calculations here. So in this case you can see that for the absorption calculation we can calculate the number of stages required, which comes out to be 1.95, and with this n, once we have obtained the n, then we can calculate the absorption factor for all other components. So absorption factor for all other components we can obtain by using this equation. So AK is nothing but the absorption factor for the kth component. Since in this case we are using the absorption factor of the key component as 10, instead of 1.4 it is 10 now, 10 divided by alpha KEA, and these different constants like bnk and bn minus 1k, these are also can be obtained by using the absorption factor. So the procedure here is by using the vapor pressure data. Vapor pressure we can get from the Antony equation, we can calculate the relative volatility, and once we get the relative volatility we can use that relative volatility in this equation and we can calculate AK. Once we get AK we can calculate bnk and bn minus 1k, and once we have obtained this, then we can write down the mass balance for vapor and the liquid phase directly in the form of fractions here. So you can see that in this particular equation, Bn minus 1 by Bnk, this is nothing but the fraction of the vapor split, isn't it? So in this way we can obtain the split fractions directly. So with this you can see that now based on the vapor pressure we can calculate in this case the relative volatility. Once we have calculated the relative volatility, we can calculate the AK, the constant AK, which is nothing but the absorption factor for kth component. Also we can calculate Bn, then we can calculate Bn minus 1, and the split fraction in the vapor phase can be obtained as Bn minus 1 by Bn, isn't it? So with that we can calculate uh, we can calculate the split fractions in the vapor phase, and 1 minus split fraction of the vapor phase, that will be nothing but the split fraction in the liquid phase. So once we get the split fraction of the vapor phase and the liquid phase, we can write down the balance equation. Now the next unit which we wanted to look at is a splitter. Remember in the flow sheet, if I look at the vapor coming out from the absorber is then given to the splitter. In the splitter the purge stream will be taken out, and the stream will be recycled back, isn't it? So how the calculations are performed in the splitter, that is given here. So the purge stream avoids the accumulation of the inlet component and impurities in the recycle stream. In the splitter, the purge rate zeta for the recycle stream is estimated. A given constraint that the mole fraction of the methane in the recycle be less than 10% is used to obtain the required purge rate. Remember in the problem statement which we have defined in the preliminary flow sheet design, there we said that the methane percentage should not go beyond 10%. So that is what we are using here in order to calculate what should be the purge rate. So in this case, this purge rate is given by zeta. So you can see that mu 52, which is nothing but the recycled stream coming out from the splitter, that will be given as zeta into mu 41. So zeta here is nothing but the purge rate. So mu 52 is nothing but the molar flow rate of the purge stream, which is given as zeta into mu 41, whereas the recycle stream is mu 51, which is given as 1 minus zeta. Whatever is remaining, that will be given as 1 minus zeta into mu 41, that will be recycled back. So now in this case you can see that this zeta value is unknown, and we can calculate this zeta value by using trial and error. So in this case we can write down the mass balance considering the recycling of different components, and then we are imposing this constant that the percentage of methane should not be more than 10%, isn't it? So with this we can calculate. So let's look at the mass balance here. So if we look at what will be the ethylene in the feed. Remember ethylene in the feed. So this is nothing but what? Mu1 EL is nothing but what? If I go back and look at the figure, mu1 EL is nothing but the ethylene which is present in the this particular stream mu1. Okay, whatever is the value of ethylene in the mu1, that is actually whatever the fresh ethylene we have fed plus whatever is coming by the recycle, isn't it? So mu1 in the ethylene, mu1 is nothing but the molar flow rate coming out from the mixture. So in this case, if we look at mu1 EL, so mu1 EL is nothing but the ethylene fed to the reactor. In this particular problem, we have assumed that there are 100 moles, isn't it? 100 moles we have started with, isn't it? So the problem statement, if you look at 100 mole per second is the feed, isn't it? So this 100 mole, out of this 100 mole, remember 96 moles will be for ethylene, then 3 moles will be for propylene, and 1 mole will be for methane. So the same information is being used here in this equation. So this 96 is coming from the feed. This is nothing but what? This is nothing but whatever we are getting back from the recycle. So recycle stream, isn't it? and that should be the feed, initial feed to the reactor, isn't it? So in this case, again we can simplify. So mu2 EL is what? Mu2 EL, if you look at the reactor equations, mu2 EL, so mu2 EL is this, which is given as 1 minus eta 1. Eta 1 is what? The conversion of ethylene. Conversion of ethylene is given as 7%. So that means 93% is unconverted. So that 93% unconverted, that particular equation is used here. So mu2 EL is given as 0.93 mu1 EL and 1 minus zeta plus 96. If we do the mass balance, this comes out to be 96 divided by 0.07 plus 0.93 epsilon. Similarly, for propylene also we can write down. So for propylene also, this will be from the recycle stream. This will be from the fresh feed, isn't it? And again mu2 PL we can write down in terms of the output coming out from the reactor. So which is, if we are assuming that 0.7% conversion, so that comes out to be 0.993 mu1 PL into 1 minus zeta plus 3. And if we rearrange, it becomes 3 divided by 0.007 plus 0.993 zeta. For methane, methane is 1% in the feed. Again mu2 M 1 minus zeta plus M, and that should be equals to 1 by zeta. And water, so water we are assuming that it is 60% in molar ratio with respect to ethylene. So we can take mu1 W as 0.6 into mu1 EL. So mu1 EL is this equation we have obtained, and if you multiply 0.6, that gives me the feed of the water, isn't it, to the reactor, isn't it? Now in this case we have obtained the ethylene, propylene, methane and water, and its amount in terms of zeta. And the condition given in the problem is what? Condition given in the problem is the fraction of the methane fed to the reactor should not be more than 10%, isn't it? So mu1 M divided by all these inlet components, which is nothing but methane, propylene, ethylene and water, it should be less than 0.1. And by using this equation, then we can calculate by trial and error what should be the value of zeta. So zeta value comes out to be 0.0038. Once we get the zeta value, then we can find out mu 52 and mu 51. So once zeta value is back calculated, we can use these two equations and we can find out what will be the, how mu 52 and mu 51 can be written. Okay. Similarly, these are the equation with respect to the vapor recovery, isn't it? Now the liquid, if you look at the liquid, so the liquid stream coming out from the flash unit is getting mixed with the liquid stream coming out from the absorber. So we can write down the mass balance equation for the mixture. So mass balance equation for the mixture can be written here. So this is the mass balance equation for the mixture. You can see that mu 42K, which is nothing but the ethanol rich stream coming out from the absorber, plus mu 32K, this is nothing but the liquid stream coming out from the flash unit. Both are added to give mu 6K. Then the next unit is the distillation column. So the first unit is the dewatering distillation column, where we are interested in removing almost 90% of the water, isn't it, with a recovery of 99.5% of ethyl alcohol at the overhead. So in this case we can take the split fraction of ethyl alcohol as 0.995 and the split fraction of the water can be taken as 0.1. So with this split fraction, we can then calculate the relative volatility of ethyl alcohol slash water. So that comes out to be 2.44. Once we have obtained this relative volatility, then we can use this Fensky equation and we can calculate the number of stages required in the distillation. So that comes out to be 8.4. Once we have obtained the number of stages, we can also calculate the distributed component split fractions, isn't it? So distributed component split fraction can be represented as, so this is the relative volatility of isopropyl alcohol with respect to water, and the split fraction of the water is 0.1 is given, and the relative volatility of the isopropyl alcohol with water can be calculated, and using this we can calculate the split fraction of isopropyl alcohol. In this manner we can calculate the split fraction of all the components. You can see that so in this case you can see that the methane, ethyl alcohol, propylene, diethyl ether, these are the light component compared to ethyl alcohol, and therefore their split fractions are almost equals to 1, whereas ethyl alcohol has a split fraction of 0.995, which we have assumed, isn't it? And we have calculated the split fraction of isopropyl alcohol by using this particular methodology, which we have extensively seen earlier, isn't it? And for water it is already given 0.1. So similarly we can do the calculations for the de-ethering distillation. Here what we are interested in de-ethering distillation column, we wanted to recover 99.5% of the ethylene in the bottom product, isn't it? Diethyl ether will be separated as a top product, isn't it? So if this is in the bottom product, what will be the split fraction in the top? That will be 0.005, isn't it? Using this again we can calculate the relative volatility, and we can calculate what will be the values for other components, and you can see that all other components like methane, ethylene, propylene, they are lighter compared to diethyl ether. They will have a split fraction of 1, whereas diethyl ether split fraction is 99.5. Ethyl alcohol is a split fraction of 0.005. So a similar calculation we can do even for azeotropic separation, which is the last distillation column. In the last distillation column we can consider this entire azeotropic composition, which is 85.4% ethyl alcohol plus 14.5% water together as one component, isn't it? And based on that we can again find out the recovery. So in this case recovery we can assume that 0.995, and based on these calculations we can even calculate how many stages are required in both these columns. So once this entire mass balance study is performed, you can see that there are around 10 streams are there. There are 7 components and there are 2 recycles. So if you look at the entire mass balance equations, around 90 linear equations we get, and these 90 linear equations we can solve using different linear equation solvers like simplex algorithm, and finally we can obtain the molar flow rate of each of these components with respect to different units. So once this mass balance is reconciled, once this mass balance is reconciled in the entire flow sheet, then the next task is we have to look at temperature and pressure. We have to see whether the temperature and pressure which we have assumed in different units, whether these are satisfying the given condition or not. So we can do the bubble point calculation, we can do a dew point calculation and check whether the temperature and pressure are below the critical limit or not, isn't it? If those constants are satisfied, then we can take this preliminary flow sheet as finalized. Otherwise we have to repeat the calculations again. So another important point to note down is, once this preliminary flow sheet is finalized, what it means that we also know the temperature and the pressure values with respect to each of these unit, isn't it? So mass balance, after mass balance, temperature values at each unit are confirmed. These values are then used for performing the heat balance. So once we know the temperature of each unit, we know how much heat is required to be added or how much heat needs to be removed. So based on that we can find out the minimum values of the utilities required. So this is what we are going to do in the heat balance, isn't it? Also if you look at the heat exchangers used for the heat transfer calculations here, so typically 10K difference is used in the heat exchanger. Between two different stream there should be bare minimum 10K difference, isn't it? So this 10K difference we try to get using the pinch analysis or some other complicated solving the energy balance equations. Okay. Again, for heat exchanger, the balance equation is given by, if you look at the balance equation for the heat exchanger, it is what? So this is nothing but mu delta H in, that is nothing but mCp dt. So this is nothing but the heat input, and this is nothing but mu delta H out. So input minus output, that gives Q. So Q in this case is nothing but the heat exchanged in the heat exchanger, isn't it? And this heat exchange in the heat exchanger can be obtained as mu summation of Yk, and this is nothing but Cp dt. So here we are assuming that the Cp is a weak function of temperature, and that is why integration is given. Typically the equation we get is, if we assume that the Cp is not varying significantly with temperature, in that case a very simple equation we get, something as mCp dt, isn't it, to find out Q. So when reactions are involved, the heat of reaction is also included in the heat balance. So if the reaction is endothermic, in that case we take the heat of reaction as negative, whereas for the exothermic reaction it is positive. Okay. So this is all about the mass balance and heat balance. In the next class we will be continuing with the cost calculations. We will be continuing with the sizing of the equipment. Thank you everyone.